Hello students, we are in continuation with unit number 11, that is some p block elements. In our last class we have seen the general trends in overall p block elements, then its general electronic configuration, and we have started with group number 13 elements, that is boron family. In that boron family, we have seen its electronic configuration, then general electronic configuration of group 13, and even we have studied some physical properties. So today we will continue with chemical properties. I hope you understand. I am Mrs. Anjali Nadgouda, Department of Chemistry, KLS Gupte PU College, Belagavi. Now let us start with chemical properties. So chemical properties mostly depends on oxidation state, that is oxidation number. So we have to first see what are the trends in oxidation state. As we have seen, these p block elements, they are showing variable oxidation state, and the common oxidation state is nothing but its group oxidation state, that is group number -10. So group number 13 elements also show maximum oxidation state is +3, because 13 minus 10 is 3. So common oxidation state is +3 due to presence of 3 valence electron that we have already seen in electronic configuration, NS2, NP1. In these elements, except boron and aluminium, other elements also show +1 oxidation state, and that we have seen in last class. Stability of +1 oxidation state increases down the group, means +3 oxidation state decreases down the group, as from aluminium to thallium. Now why it is? Due to inert pair effect. This is already we have learnt in last class, that is p block elements, they are having different chemistry or different properties or changing properties. It is because of inner core electrons, how they behave, right? And here is one of the reason. Due to inert pair effect, the stability of +1 oxidation state increases down the group. Now in this, the minimum oxidation state shows ionic compounds, whereas maximum oxidation state shows covalent compounds, and hence +1 oxidation state compounds are more ionic than +3 oxidation state. Now let us see another properties. In trivalent state, trivalent means +3 oxidation state, around the central atom only 6 electrons are present in their compounds. Now how it is? 3 from the central atom and 3 electrons from the attached atom, or which are the around atoms. Is it? So total 6 electrons are present, means they are having or they are deficient in one electron pair, that is 2 electrons are less to complete its octet in their valence shell, and hence these elements, they have the tendency to accept a pair of electrons to achieve stable electronic configuration, and therefore they behave as Lewis acids. In last year we have already studied the atom of the element which accepts a pair of electron to complete its octet. It acts as Lewis acid, and the one who gives the electron or donates the electron acts as Lewis base, right? So example is BCl3 accepts a lone pair of electron from NH3 to form the addition compound, that is BCl3NH3. Now here the compound which is formed, we can show it like this: BCl3 arrow NH3. Now here nitrogen is giving the pair of electron to boron, and hence the arrow mark is shown like this. So this bond we call it as coordinate bond or dative bond, and this equation is given in textbook. So please refer the equation in textbook. Right? Now in this B, boron is having 3 electrons in outermost shell. 3 electrons are shared from chlorine, 3 chlorine atoms. So total number of electrons around boron is 6, and 2 electrons are accepted from nitrogen. So this is how boron complete its octet, that is 8 electrons. Means it achieves the stability, or it becomes stable, and hence this acts as BCl3 acts as Levy's acid. Now this tendency, is it remains same? No. This tendency of becoming Levy's acid or to behave as Levy's acid decreases with increase in size down the group. Means as we move down, the behavior of Levy's acid decreases. Okay, now here one more question comes, that is aluminum forms trivalent ion but not boron. Explain. Okay, now this is due to small size of boron, the sum of the first 3 ionization enthalpies is very high. Now sum of the first 3 ionization means what? The energy required to remove the 3 electrons one by one is called as what? Sum of the first 3 ionization enthalpies is very high. Why it is high? Because its boron is having very small size compared to the other elements. Now this prevents it to form plus 3 ions and forces it to form only covalent compounds. Means the question is of formation of ionic compounds. Boron can share the electrons but cannot give the electrons. Okay. But as we move down from boron to aluminium, the sum of the first 3 ionization enthalpies of aluminium considerably decreases. Means it becomes less, and hence for aluminium it is easy to form the ionic compounds. In trivalent state, that is in plus 3 oxidation state, most of the compounds are covalent. Covalent means what? They are formed by sharing the electrons, not by giving or accepting the electrons. And they are easily hydrolyzed in water. Hydrolyzed means what? They can be dissolved in water. Okay. So species like when it is dissolved in water, they are forming either hydroxides or hydrated compounds like MOH4 or MH2O6. Now these are having special geometry, that is either tetrahedral or octahedral, but these compounds exist in aqueous medium. Okay. Now here also the exception is there, that is boron. Boron only forms MOH4, that is BOH4. Okay, boron tetrahydroxido or tetrahydroxy. But boron cannot form H2O6, that is BH2O6. Okay. Now what is the hybridization of metal in this? M stands for metal, or M stands for the element in group 13. So in MOH4, hybridization state of metal or M is sp3. Now here this is the ionic compound which is having -1 charge. Okay. So what is the hybridization? Is sp3. Whereas in H2O6, that is in octahedral hydrated compound, it becomes sp3d2. So here is an example of AlCl3. When AlCl3 is acidified in aqueous solution. Acidified in aqueous solution means acid is added in presence of water or dilute acid, forms an octahedral ion, that is AlH2O6 3 plus. In this hybridization state of aluminium is sp3d2 because 3d orbital is involved in hybridization. Now how 3d orbital? Because we have seen in aluminium atomic number 13. So 1s2, 2s2, 2p6, 3s2, 3p1. Now here third shell is the valence shell, means there is 3d orbital but it is not filled, means no electrons. So we write 3d 0. Now 3d 0 means what? Presence of d orbital is there but there are no electrons. That's why we are not showing. But now in excited state this s electron can jump to d and hence d orbital can be involved, and this is how sp3d2 hybridization takes place. Okay, yes. Now let us see how they react with oxygen or halogen, etc. Reactivity towards air. Air means oxygen and nitrogen. Now in this there are some specialities or there are some characteristic properties from element to element. So boron is unreactive in crystalline form, means boron does not react in crystalline form. Then when it reacts, whenever it is in the powder form. Okay, yes, okay. Then aluminium forms a thin oxide layer on the surface which protects the metal from the further attack, means aluminium also directly does not react. It forms an oxide, means oxidation takes place, and this is how one protective layer is formed on the surface which does not allow the further attack of oxygen or nitrogen. Now let us see how amorphous form of boron and aluminium reacts. Now it requires heating. Okay, so amorphous boron and aluminium metal on heating in air form oxide. Which type of oxides? These are trioxides, B2O3 and Al2O3, aluminium trioxide and boron trioxide. So general equation for this is 2E plus triso2 gives E2O3 solid. Okay, now this where E is element from group 13. Okay, so if we put instead of E as B, so B here, B plus triso2 gives B2O3, like that Al plus triso2 gives Al2O3. Okay, similarly with dinitrogen, because air contains nitrogen also, so dinitrogen means N2. At very high temperature they form respective nitrides, that is En. So these are the general equations. Now how these oxides are? Again these oxides, they show various properties. So non-metal oxides are acidic, whereas metallic oxides are basic in nature. Is it? So boron oxide, that is B2O3, is acidic, whereas metallic oxide, these are basic oxides. Then aluminium and gallium oxides are amphoteric, means they react with acid as well as base, whereas indium and thallium oxides are basic in nature. There is one more thing, that is B2O3 is acidic oxide and it reacts with basic oxides forming metal borates. Okay. Let us see how they react with halogens. Halogens means X2. So X is fluorine, chlorine, bromine, iodine, and E is element. So here is the general equation. All they are forming trihalides, EX3. Exception is there, TLI3, that is thallium iodide cannot be formed. Okay. So TLI3 is an exception. Otherwise, we can use the general equation to form the trihalides. Now, all boron trihalides except BF3 are hydrolyzed to boric acid. This is already we have seen in last slide. That is, the trihalides, or in trivalent state, the compounds are easily hydrolyzed. Is it? So BX3 plus 3H2O gives BOH thrice. This is called as boric acid, which is also called as orthoboric acid. Again, we can write the formula as H3BO3 also. H3BO3 for boric acid, or BOH thrice. But this is non-protonic acid, means which does not give H ions. Okay. Plus, now after forming boric acid, again it forms what? HX, that is hydrogen halide. Okay. So after hydrolysis it gives boric acid. Now X is what? ClBrI. Now here which one is not reacting? BF3 is not showing the reaction. Otherwise all trihalides, they show the similar reaction. Okay. Now how this BCl3 exists? It exists as monomer. Means what? Last year we have studied the structure of BCl3. It is like this. That is sp2 hybridized, and hence the angle is 120 degree. Right? BCl3. This is how we have studied the structure of BCl3. But aluminium chloride does not form monomer, it exists as dimer. Now why it is? To achieve the stability. So how this exists? Just see, one Al is bonded to 3 Cl atoms. Again this Al bonded to 3 Cl atom. To achieve the stability, why stability? Means one electron pair is deficient, and this can be accepted by chlorine, and hence the bond is formed between aluminium and chlorine, which we call it as dative bond or coordinate bond, and this is how it exists as dimer. Dimer means di means two, mer means chain, so it is in the chain form. Two Cl atoms, they are in bridge form, linked to two Al atoms. Now let us see the reactivity towards acids and alkalis. Boron does not react with acids and alkalis even at a moderate temperature. But aluminium shows the amphoteric nature, that is, it dissolves in mineral acids. Mineral acids means HCl and aqueous alkalis. Okay, so we have to see the two different reactions. In both the reactions, hydrogen gas is liberated. Okay, so reaction with acid, aluminium dissolves in mineral acid, that is dilute HCl. Al plus 6 HCl gives, now here aluminium behaves as ionic form. AlCl3 is formed, that is Al plus 3 and 6 Cl minus. So it is in the form of ions. Now after combining these ions, you can find out it will form this Al, and this Cl gives AlCl3 plus hydrogen gas. Okay. What happens to concentrated nitric acid? Concentrated nitric acid renders aluminium passive by forming a protective layer on the surface. Means once only it reacts to form layer on the a protective layer on the aluminum surface, and further action is rendered or further action is opposed. How aluminum reacts with alkalis then? Yes, it reacts in aqueous medium, means in presence of water, forming a complex compound, that is sodium tetrahydroxoaluminate. Here oxidation state of aluminum is +3, hence it is shown with Roman 3. Next year you are going to learn these type of compounds which are called as coordinate compounds or complex compounds. So aluminum reacts with alkali. Here the example is taken of NaOH, aqueous NaOH, that is in presence of water. So Al plus NaOH plus water gives NaAlOH4, that is sodium tetrahydroxo. 4 hydroxyl groups are there, therefore tetrahydroxo aluminate. As this complex is having negative ion, therefore aluminate 3. And here also in this reaction hydrogen gas is liberated. Means aluminum, when it reacts with acids or alkalis, it liberates hydrogen gas, but boron does not show any reaction with acids and alkalis. Now from all this you might have seen that boron shows different properties than that of other elements present in the group. Is it? This property we call it as what? Anomalous behavior. And we know that the second period elements are showing the anomalous properties or anomalous behavior. Now why it is? There are 4 reasons. That is due to extremely small size. So as they do not contain any d orbitals, and hence they are having yes, this is one of the reason, that is absence of d orbital electrons. And why we can say due to extremely small size? Because only two orbits are present, that is first shell and second shell, hence they are having very small size. Then high nuclear charge to size ratio. Similarly, high ionization enthalpy. So these are the 4 reasons. Because of these 4 reasons, boron shows different properties than that of the remaining elements in that group. Now let us see which are the properties in which boron differs. Okay. So boron is typically non-metal, whereas other members are metals. From aluminium to thallium, all are metals. Boron is bad conductor of electricity, whereas other metals are good conductors. And we know that the street lines, that is power distribution lines, are made up of aluminium, because it is lightweight metal as well as good conductor of electricity. Yes, this we'll see in application also. Now boron shows allotropy. It exists in 2 different forms, that is crystalline and amorphous. This we have seen in reaction with air. Is it? Crystalline form does not react with air, whereas amorphous boron reacts with air to form oxide. Is it? Aluminum is soft metal and does not exist in different forms. Means it exists only in one form. Boron forms only covalent compounds, whereas other elements of group 13 even form ionic compounds. This is also we have seen, because boron is having very small size, it cannot give its electron. It can only share the electrons. Okay. The hydroxides and oxides of boron are acidic in nature, whereas those of other elements are amphoteric and basic. Now why it is? Because boron is typically non-metal, whereas other elements, aluminium and gallium, are metalloids, whereas they are behaving like non-metal also sometimes. Therefore we can say they are metalloids, and indium and thallium, they are perfectly metals. Even aluminium is metal. So the oxides are hydroxides or oxides are maybe amphoteric and basic in nature. Trihalides of boron, that is BX3, exist as monomers. On the other hand, aluminium halides exist as dimer. This is already we have seen. Now one more property, dilute acids have no action on boron, but others liberate hydrogen from them. Okay. And the last but not least, we can say very important property of boron is boron exhibits maximum covalency of 4, while other elements exhibit maximum covalency of 6. And this we have seen in the formation of compounds like BOH4. Boron can form tetrahydroxo, but it cannot form BH2O6. Right? But aluminium can form AlH2O6. So these are the properties in which boron differs from other elements. The questions are two different questions. One is why boron shows anomalous properties. There you have to write the reasons. Whereas how boron differs from the other elements, then you have to write the main points of difference. Okay, let us see uses of boron and its compound. 2-3 I will explain, remaining you can read it. Boron fibers are used in making bulletproof vest and light composite material for aircraft. Now this bulletproof, especially it is used in military to protect. Then boron 10 isotope has high ability to absorb neutrons, hence it is used in nuclear industry. Then very special use of boron is to dope with silicon and germanium to improve its electrical properties. I hope you have heard about the semiconductors, p-type and n-type semiconductors. In that, boron is used to dope with silicon and germanium. Okay. Even our glass apparatus used in laboratory, that is made up of borosil, in that boron is used. Okay. So other properties you can read it. Let us see the uses of aluminium. Important uses of aluminium I have given. As aluminium is good conductor of electricity, it is used in electrical transmission lines. Then for transportation, that is automobiles, aircraft, trucks, etc., the body parts are made up of aluminium because it is lightweight and it can be hammered into thin sheets. Is it? Then as a packaging material, that is cans, especially the cold drink cans, etc. Then we can pack the food in aluminium foil. Then even cooking utensils which we use in our day-to-day life, they are made up of aluminium. Even potash alum, which is the composition of aluminium, is used in water treatment, that is specially for settlement of the dust particles in water. Okay. So here the group 13 elements part is over. In next class we will study group 14 elements. The other part, that is some important compounds of boron, is not taken because that is deleted in 30% reduction of syllabus. Okay, you can go through it for additional information. Thank you.